Hello viewers, welcome to this section of this course, Building Real-Time Recommendation Engines with Spark. In this section we'll learn about the model-based approach of collaborative filtering, moving away from the heuristic-based similarity approaches. Also, we will focus on implementing the model-based collaborative filtering approach using Spark. In the previous section we learned about implementing similarity-based collaborative filtering approaches such as a user-based collaborative filtering and content-based collaborative filtering. Though similarity-based approaches are a huge success in commercial applications, there came into existence model-based recommender models such as matrix factorization models, which have improved the performance of recommendation engine models. This section will demonstrate the following topics: about Spark 2.0, Spark Core, setting up Spark, collaborative filtering using alternating least square, model-based recommender systems using PySpark, the recommendation engine approach, model evaluation and selection with hyperparameter tuning. Let's move on to the first video of sections about Spark 2.0. In this video we'll learn about a few topics. They are Spark architecture, Spark components. As a general-purpose computing engine, Spark can be both run as a standalone mode and as a cluster mode. Spark can easily be integrated with Hadoop platforms. Spark, with its in-memory data processing capability and easy-to-use APIs, allows us to efficiently work on a wide range of large-scale data processing tasks, such as streaming applications, machine learning, or interactive SQL queries over large datasets that require iterative access. Spark can be easily integrated with many applications, data sources, storage platforms, and environments, and exposes high-level APIs in Java, Python, and R to work with. Spark has proved to be broadly useful for a wide range of large-scale data processing tasks, over and above machine learning and iterative analytics. Spark architecture. The Apache Spark ecosystem contains many components to work with distributed, in-memory, and machine learning data processing tools. Spark works on a master-slave architecture. A high-level architecture is shown in this diagram. The Spark cluster works on the master-slave architecture. The Spark core execution engine accepts requests from clients and passes them to the master node. The driver program in the master communicates with the worker node executors to get the work done, as shown in this diagram. Spark driver program. The driver program acts as a master node in a Spark cluster which hosts the Spark context for Spark applications. It receives the client request and coordinates with the cluster manager, which manages the worker nodes. The driver program splits the original request into tasks and schedules them to run on executors in worker nodes. All the processes in Spark are Java processes. The Spark context creates resilient distributed datasets, RDD, an immutable distributable collection of datasets partitioned across nodes, and performs a series of transformations and actions to compute the final output. We'll learn more about RDDs in the latter sections. Worker nodes. A worker contains executors, where the actual task execution happens in the form of Java processes. Each worker runs in its own Spark instance and is the main compute node in a Spark. When a Spark context is created, each worker node starts its own executors to receive the tasks. Executors. These are the main task executioners of Spark applications. Spark components. In this section we'll see the core components of the Spark ecosystem. This diagram shows the Apache Spark ecosystem. Great! We've successfully learned about Spark 2.0.